Afternoon, young ones. How you doing?
We are fine, thanks. How are you, sir?
I'm all right. The lesson for today is transistor biasing. Ne? We learn about how to bias a transistor. But what is transistor biasing? Transistor biasing is the process of supplying the appropriate DC voltage and current to a transistor in order to make sure that it functions or it operates in a desired region. Ne? Now, why do we need to bias a transistor? To make sure that it's stable when it operates. To make sure that the amplified signal is also stable, it doesn't get distorted. But I will elaborate on that one a little more as we go about. Ne? Let's look at the first way of biasing a transistor. They call it a fixed bias. If the transistor is connected like this, we'll only focus on an NPN transistor. Ne? The supply voltage or the battery will be connected here, and you're going to call it VCC. Ne? This is RB or the base resistor. This is RC, the collector resistor. You're going to take your output to the next circuit here. Ne? This is V out or the output voltage. You're going to connect your signal here. This is your signal input. We must put capacitor here as well. I'm going to call this C1. I'm going to call this one C2. Transistor 1. You still remember this is the collector. This is the base. And this is the emitter. This sign or symbol means it's connected to ground. Or the negative wire will be connected here. The red wire will be connected here of the battery. This configuration is known as fixed bias. I won't go into details on a fixed bias because we won't be using fixed bias. I'm just showing you how it is configured if it's a fixed bias. But now, if you connect a resistor here in the base, we'll call it RE, because the emitter resistor. It is no longer a fixed bias. But what is it? It's emitter bias. The emitter bias is a little more stable than the collector. Not the collector. Then the fixed bias. So the types of bias that you have a fixed bias, you have an emitter bias, also have a collector to base bias. And the fourth one, that's the one that you'll focus on this course. We call it a voltage divider bias. Let me show you the last configuration. If you disconnect your resistor from the base, from a VCC, and then you connect it here to the collector. This is your supply voltage, and here there should be nothing. This will be your number 3 type of biasing. Oh, this is RB. This is the collector to base bias. We connect the resistor here to form the feedback from the collector back to the base. Now let's talk about this one. We call this one R1, we call this one R2, we call this one RC, because it's connected to the collector. We call this one RE, because it's connected to the emitter. And then our input signal, it looks ugly. And then our input signal will be a signal input. Go through C1, and then our output will be connected here. V out. Now this will be our R2. This is the voltage divider bias, also known as self bias. This one, it is widely used. That's why I want us to focus on this one, because it is widely used and we will be utilizing this one in our projects. So I will elaborate further on this one. But before I talk about this biasing, let me first talk about the characteristics, the output characteristics of a transistor. Okay, now look at the board. I said that we bias a transistor in order to make sure that it operates in the desired region. We have the transistor have 3 regions, which is the cutoff region, the active region, and the saturation region. In the cutoff region, or when the transistor goes to the cutoff region, it means that it is off. It's like it doesn't exist, or it's like a switch that is switched off. You know the switch most on the wall to switch the light on and off. Yes. In the cutoff region, it's like the transistor is off. That's when the beta current, not the beta current, that's when the base current is equal to 0. Automatically, the collector current will also be equal to 0. In that case, both junctions, you remember the junctions, the transistor junction, the J1 and the J2, or the base collector and the base emitter junctions. In that state, both of them, they are reverse biased. Yes. In that region, the transistor behave as an open switch. Then we have an active region. You remember the uses of a transistor. You use a transistor as a switch and as a amplifier. In that state, or in that region, active region, that's when the transistor operates as an amplifier. So if you bias a transistor, you supply it with a DC voltage to make sure that it remains in this region. It doesn't fluctuate even when the temperature around it changes. But how do you make sure that the transistor operates in the active region? We said we're going to talk more about the voltage divider bias and RC. In order to make sure that the transistor operates at this point, we want to make VCE. I'm out of space now. Let's remove this. VCE is the voltage that is found here. Here it will be positive, it will be negative. The voltage between the collector and the emitter. It's a collector emitter voltage must at least be equal to half of the supply voltage. Let's say here is 12 volt. Here we must have at least 6 volt. For this transistor to operate at this point, which is the Q point. At the Q point, that's where the transistor is stable. The Q stands for quiescent. Quiescent means stable or quiet. It means the transistor here operates nice. Ne? We avoid that the transistor shouldn't maybe at least operate at this region. If it operates here, that means now our signal will come like this. So if the signal come in like this, it will be clipped. Ne? You see already, because it cannot go below 0. If it get amplified, yeah, it will go like this. This part will be clipped. This part won't exist. Let's say you play music. There's a part in music that you won't hear. Does it make sense? So we try to make sure as much as possible that it stays here. So for the transistor to operate at this point or in that active region, we make sure that VCE at least is equal to half of the supply voltage. Ne?
Yes, sir.
And then the third region is a saturation region. At saturation, okay, before we go to saturation, as you can see in this graph, that when the base current, this is IB, this is IB or base current, all of this. Sorry about that. This is IB. When IB increases 10 microamps, we get 10 milliamps for the collector current. The base current is here, ne? It goes to the base IB, and the collector current flows from the source through this resistor to the collector. Ne? This is IC, this is the collector current. But now, where do we get this 10 milliamp from? We get it by saying collector current is equal to beta multiplied by the base current. Where do we get beta from? We get it from the transistor specification. When you buy a transistor, they will write there the value of beta, but usually it's between 10 and round about, let's say 500. Usually we assume that beta is equal to 200. Nah. So when IB is 0, beta multiplied by 0 is equal to 0. Nah? That's why when the base current is 0, the collector current will also be equal to 0. So the transistor will be off. So at saturation, when you say something is saturated, the statement is no longer true. Nah? That's when now IC is equal to VCC all over RC plus RE. RC is here and RE is this one. Then in that state, the transistor is operating in saturation region. Eh? In saturation region, that's when the transistor let the maximum current to pass through from the collector to the emitter. And in this case, the transistor behaves as a closed switch. But now, when do we use a transistor in saturation and in cutoff? Most of the time, that is applicable in the digital electronics, when the transistor is used to switch the signals on and off, on and off, on and off. But now, when do we use a transistor in the active region? Maybe we want to amplify voltage, or we want to amplify a song. You know, most the artists, when they sing on stage, what do they use? A microphone. Eh? A microphone have what? Have a transistor inside. That transistor is the one that amplifies that voice so that people can hear. Do you understand?
Yes, sir.
Here in saturation, that's when IC is equal to maximum. And VCE is equal to 0 volt. Here IC is equal to 0. And VCE at the cutoff, VCE is equal to VCC. Now, we're not going to do calculations, but yeah, okay. Now let's use a voltage divider bias to see how are we going to bias a transistor in the real world. So resistor. Out. This is R.
1.
This is R.
2.
This is R.
C.
This is R.
E.
Let's supply this transistor 12 volt. Now we want to bias this transistor in such a way that the Q point or the operating point is in the active region. We want to use this transistor to amplify the signal. Our IC will be here, our VCE will be here. We know that at this operating point, VCE is equal to half VCC. So which means now we already have one value. We know that VCE is equal to half VCC is equal to 12 over 2, and that is equal to 6 volt. Let me make a space here. Now let's assume that this is a silicon diode. So our V out. So we already have VBE is equal to 0.7 volt. And we are given that beta is equal to 200. What is beta? Beta tells us that this transistor is capable of amplifying the current by 200. So if you put 1 milliamps here, you are surely to get 200 milliamps on the outside. Does it make sense?
Yes.
Yes, beta is a current amplification. Now what next? Where do we go from here? Now let's just decide how much amps do you want to allow to go through this transistor. The young lady says 2, then we're going to say milliamps. You said 2, mustn't We decided we want to allow 2 milliamps to flow as our collector current. Remember, if you allow too much current to flow here, what's going to happen to the transistor? It's going to burn. The transistor is going to burn. So you must also check the data sheet that how much current can this specific transistor can handle. So we choose or we decide how much current we want to allow to flow through this collector, so that you can come up with the value of a resistor that you can put here as a RC. So now we also have another value now, which is IC. We can also have a look at these formulas there on the side, so that you can determine the value of the resistors and the capacitors and stuff. So now, in the book I read, they said VE, which is the voltage at this point, we must at least allow VE to be equal to 10% of VCC. What is 10% of 12? It's 1.2 volt. So we already have VE, that VE is equal to 1.2. Oh, it's written here, so let's leave it this side. So now we know VE, IC, VBE, VCE. What else can we get? We can get VB, which is the voltage at this point. According to this formula, VE is equal to VB minus 0.7 volt. So we have VE, let VE is 1.2, VB not known. That's what you're looking for. If we manipulate this formula, we bring this across, then VB is equal to 1.2 volt plus 0.7 volt. And that gives us 1.9 volt. Equal to 1.9 volt. Now with VB, VE, what else? VCE, we can calculate the values of the resistors using these formulas here. We can also calculate IB. This one. Because we have beta and we have IC. IB is equal to, as the formula, IB is equal to IC over beta. And then this is equal to 2 times 10 to the power minus 3 all over 200. Now IB is equal to 10 microamps. Yeah. Let me write these values this side. Now with all these values, we can start calculating the resistors. This one is grounded. Let's start by calculating RE. RE is equal to, R is equal to V over I. What is VE? Didn't you calculate VE? VE was equal to 1.2 volt. So you have 1.2 volt divided by, can you see here that IE is approximately equal to IC, and IC is 2 milliamps. It gets 600 ohm, and 600 ohm is approximately equal to 560 ohms. Now we have RE. Remember that you have tolerance for resistors. Re sharp, RC. Do you have VC? We have VCE, VCC, IC. Yes, VCE is equal to VCC minus IC RC plus RE. Ne? VCC is 6 volt. VCC is 12. IC is 2. Minus 3. RC is what we're looking for, ne? RE is 560 ohms. Let's get back to work. 6 minus 12 is minus 6 all over 2 times 10 minus 3 is equal to RC plus 560. RC is equal to 3000 minus 560. And then we get 2.44 kilo ohm, which is equivalent to 2.2 kilo ohm. Now we have RC is approximately 2.2 kilo ohm. Now we need this R1 and R2, so we'll go with VB is equal to R2 over R1 plus R2 multiplied by VCC. Yeah?
Yes, sir.
And then we know that, let me just write this one for the space. We know that VB is equal to 1.9, mustn't it? Now we just assume that R2 is equal to 10k or 10,000. Then we're looking for R1 plus times 10 to the power 3. Let me do the same here. So that's VCC. Now we'll divide with 12 on both sides. 158.33. Yes, is equal to 10,000 over R1 plus 10,000. Then we multiply with denominator on both sides. Then you're going to have 158.33 R1 plus, this is times 10 minus 3. 158 R1 plus 1.58 times 10 to the power 3 is equal to, and therefore R1 is equal to divided by R1 is equal to 53 kilo ohm. We said R2, we guess it to be equal to 10 kilo ohm, and R1 is equal to, which value is closest to 53 kilo ohm? Let's say it's 56 kilo ohm. So if we can get this type of a transistor and put these resistors like this, connect it like this on a breadboard, put the resistors of these values. We can almost operate this transistor in this active region. You see, how do we go about doing this in real life?
Yes, sir.
Yes. Now when we do this practical, we'll also learn how to calculate the value of these capacitors. Do you understand?
Yes, sir.
Yes. But here, you must also put another capacitor here. This. I call it CE. I will show you practical why do we need these capacitors. But they are just used to block DC, so that DC doesn't interfere with the output signal. Here the noise as well from the outside world. When you speak on the microphone, you must only allow the voices to pass, and then we block DC. Remember that capacitor allow AC to pass and it blocks DC. The same thing this side and this side. This is how you bias a transistor.